Hi everyone. So this is our first video for chapter 5, Newton's laws. We're going to start off today talking a little bit about what the four fundamental forces of the universe are, and then we will continue on into general forces, starting Newton's laws today, and we'll continue them as we go. So first, we have the four fundamental forces. First force we have is the strong force, right? Strong force has this relative strength here, right? So this relative strength we're talking about, we're comparing all of the forces and their relative strength on an object. Kind of like if it were to affect a proton, how strong would it be relative to the others? So strong force being the strongest, we're going to call that 1. Okay, it has a relative strength of 1. Now, the range of this strong force, right? So this strong force is the strongest force in the universe, but it only acts on a very small scale, right? It is only acting at 10 to the negative 15th meters, so it's got a very limited range. However, it doesn't affect you and I every day, right? This is not something that we are working on 10 to the negative 15th meters. 10 to the negative 15th meters is a femtometer, and a femtometer is about the size of a proton or a neutron. So what this does is this affects particles called gluons and hadrons. So gluons are these small that confine quarks. A group of 3 quarks will make a hadron. Hadrons are your protons and your neutrons. And depending on which 3 quarks you have will determine if you have a proton or if you have a neutron. Now, this also, the strong force responsible for gluons and confining quarks, it is also responsible for binding those hadrons of the nucleus together. Because the protons should repel each other immediately, right? Protons are all positively charged particles. We know that like charges repel, opposite charges attract. But in the nucleus, we have a lot of positives all crunched together, and they're not bonded by negatives. They're bonded by this neutral neutron, right? So you have a bunch of positives and then a bunch of neutral particles. They should just rocket away. Well, the strong force prevents them from doing that. That holds all of the protons and the neutrons together in the nucleus so that the nucleus isn't constantly just exploding, and then the nucleus wouldn't even exist. Right? So that's what the strong force does. The electromagnetic force, that is the next strongest force that we have. That is a relative strength of 10 to the negative second, so 1/100th, right? So that has a long range of force, right? It depends on the strength of the source, how strong it's going to be, and how strong that is going to, or how far that is going to go, right? So electromagnetism is something that you guys are probably fairly familiar with. It affects charged particles, right? Positive and negatively charged particles called ions. Cations are positive, anions are negative. The electromagnetic attraction between atomic nuclei and their orbital electrons holds the atom together, right? The positives and the negatives are attracted together, so that holds them in place. That's part of what the electromagnetic attraction is responsible for. So on a small scale, it can hold atoms. I guess it helps the nucleus hold the electron cloud in place so it doesn't get too excited and explode off. That is the same force, however, that is responsible for magnetic fields around our planet or around our sun. That is also caused by electromagnetic forces. And chemical bonding. Chemical bonding is also caused by electromagnetic force. You've got covalent bonds, ionic bonds, even metallic bonds are all caused by the sharing of electrons with the electromagnetic force. So without the electromagnetic force, we'd have no molecules, right? No not particles, no atoms would ever bond. So this is basically the foundation of any chemical bond that has ever happened. So, it is a relatively strong force, the second strongest force in the universe, other than the force that holds all of matter together. But it does diminish by this inverse rule, right? It diminishes inverse square law. It diminishes by 1 over r squared. So as you increase the radius, it will diminish by a factor of 1 over that radius squared. The third strongest force that we have is called the weak force. You'd think the weak force would be the weakest, but it's not. The weak force is also on a very small level. Now, the weak force is on an even smaller level than the strong force. Strong force works on 10 to the negative 15th. The weak force works on 10 to the 18th, negative 18th meters. Very, very small. So the weak force is responsible for quarks. So we talked about how these quarks are not really controlled, but they are kept together by the gluons, right? And that is from the strong force. Sorry, my dogs are walking around the house and you can hear their nails on the floor. So the strong force has the gluons and that form hadrons, that form protons and neutrons. But the gluons themselves are manipulating quarks. Well, the weak force is actually responsible for what we call the flavors of quarks. Quarks have 6 flavors. They have up, down, top, bottom, strange, and charm. So they have 6 flavors, and those can be arranged in many different varieties. But the up and down quarks are the ones responsible for protons and neutrons. And if you get 3 of those quarks in the right order, you'll get a proton. If you flip it around a little bit, then you can get a neutron. Yeah, but this weak force can actually change the flavor of a quark from up to down, top to bottom, strange to charm, or vice versa. And that can change your proton to a neutron or your neutron to a proton, back and forth. It usually changes protons to neutrons. This is the driving force that causes radioactive decay. So what can often happen is in these large atoms, a proton will flip to a neutron. That is caused by the weak force. The weak force causes that instability in an unstable atom, and that neutron will fly off, and that is what is radiation, right? And then now that it has 1 less proton, now it has moved down on the periodic table, and most radioactive elements will work their way slowly down until they get to lead, which is 92, I think, is the element 92 on the periodic table. Pb for peanut butter is its elemental symbol. So that happens naturally through radioactive decay. Now, there are other ways for atoms to digress down the periodic table. One is nuclear fission. Nuclear fission is when an atom is so big that it actually breaks apart, right? So then it's actually splitting into 2 smaller atoms. That usually splits rather evenly. So you wouldn't split from a large atom down to 2 leads. That will split down to something much smaller than that. But radioactive decay will take a natural progression down the periodic table to reach lead. Some of those elements are a little more unstable than others, so some actually might get skipped, or they exist for a very small amount of time before they move on to the next one. But the weak force is what causes radioactive decay. Again, very small, very limited range that is operating on. Also relatively small. That is 10 to the negative 6. So that is 1/millionth of the strength of the strong force, whereas the electromagnetic force was just 1/100th. So now we're down to 1/1,000,000th. And then we get to the gravitational force, which is 10 to the negative 38th strength. You would think that gravity would be relatively strong because everything in the universe experiences gravity, right? Well, it's actually the weakest force in the universe. It operates at a very long range, Again, the strength depends on the source. Electromagnetism is caused by a charge, that's determined by how many protons and neutrons relatively are in an atom. It can also be caused by a collection of electrons or a collection of protons, and that can cause a charge in an area in an object as well. Now for gravity, that's different. This is caused by mass. So just the sheer presence of matter or of mass can cause gravity to take place, right? Anything that has mass has a gravitational pull. You just need a lot of mass to get a lot of gravity, right? Because it's so weak. If this was a really strong force, then this pin could possibly have a very strong gravitational pull. But since it doesn't have a whole lot of mass, it doesn't have a whole lot of gravity. Thankfully so, because if that were the case, it would be really hard to stand up from a chair, right? Especially if you have a really heavy chair, just standing up from it would be difficult. Along with all of the other furniture on the room, either they would be pulled to me in my gravitational pull, or I would constantly be pulled to them, and it would be a nightmare to even navigate, right? So it's actually a really good thing that gravity is so weak, because we don't want every object to have its own gravitational pull that we need to worry about navigating. Only the big, large bodies are going to have a gravitational pull that needs to be worried about. So the gravitational force, it's the dominant interaction at the macroscopic scale. When we look into space and in the universe, and we're looking on the scale of planets, asteroids, stars, and then we go up to solar systems and then galaxies, and then even bigger than that into clusters. Gravity is the dominant force at that range. Because we have so much mass in some of these large bodies that it is actually able to propagate out to a much larger distance. Mass and energy warp space-time, and that is how this actually works. I wasn't going to get into a space-time discussion, but mass and its presence of mass in space-time causes a warp in space-time that kind of causes things to move towards that source of mass or energy. Now remember, mass and energy are the same according to E = mc squared. Mass is basically just pocketed up energy, and energy is kind of all of that energy in mass that could be released. So you can actually use E = mc squared to find out how much energy you have in your mass. If you just take your mass, I think I'm about like 70 kilograms or so. So if you take 70 kilograms times c squared, which is the speed of light, squared, that's how much energy you would get in joules. And it's a lot of energy. There is a lot of energy in mass, in matter. Because that equation is assuming that matter is completely obliterated and turned into pure energy. And matter has a lot of energy packed into it. But that mass and energy can warp space-time, and that's what causes gravity to get things to get pulled by a gravitational force. The particle that these manipulate is called a graviton. We've never actually discovered a graviton. It's kind of a theoretical particle. We don't actually know that it exists. Some theories say that it doesn't exist. Some theories require it to exist. That is why none of these theories have been moved on to law. But we do think that the graviton could be discovered using the Large Hadron Collider. That's one theory that we could discover using the Large Hadron Collider. The collider is actually trying to fill out the standard model of particles. They already had a great success in the boson field, and the Higgs boson. That was a big deal several years back. But the graviton has yet to be discovered. Me personally, I don't know that I really have a dog in that fight. I don't know that there is a graviton. I kind of lean towards no. Just because we know how gravity works, it's actually just mass and energy warping space-time. The other three forces have nothing to do with space-time. So I think that this force might work separately than the other ones. That's just my opinion as a high school science teacher, so that all of this can be taken with a grain of salt. Okay, so those are the four fundamental forces. Now let's keep on moving. What do we have next? Everyday interactions. So let's look at these everyday interactions and look at the kind of forces that are happening here. So first we have letter A here. We have someone pulling a spring. This would be caused by electromagnetism, believe it or not. So contact forces are the result of electromagnetism. Pulling is allowed, right? You can pull on that spring because the atoms are actually holding together and allowing that pull to happen. Then just the design of the spiral allows it to flex. But the fact that the electromagnetism is holding the bonds together and not just shattering as soon as you pull it, right? That is a function of electromagnetism. Also, B and C here. We have a woman pulling a wagon with a child and a football player kicking a ball. These are both repulsion forces, right? The woman is, well, I guess that's not really repulsion for the woman, but she's pulling that wagon. The atoms are holding together. So that is electromagnetism. The player is kicking the ball. Technically, he's not actually touching the ball, right? He's getting extremely close, and the electron clouds that cover all of his atoms of his shoe when he kicks are actually repelling the electron clouds of the football. And if you send your field against the football's field harder, then it will move away faster. And then there's the geometry of the football that gets all involved, and then it gets crazy. But all of these, this top row is electromagnetism, pushing the ball right with that foot, and then pulling the spring and the wagon. Pushing and pulling are all electromagnetism. Now, letter D, we have a field force, right? That looks like a small mass moving towards a larger mass. Now, remember we talked about mass causing an inherent force. That would be gravity. So letter D, this is an example of a gravitational force, right? We have small mass moving towards a big mass because the big mass would have a stronger gravitational pull. Letter E, this isn't something that we've gone over in class yet, but you may have seen this before. The letter Q can symbolize an electric charge. It seems like we have a small negative charge moving towards a large positive charge. This would again be electromagnetism. Now, the reason this is down here is because this is a field force, not a contact force. So field forces, two objects that are nearby seem to act on their own, but we actually know, using science, we can figure out that there is more at play there. There is a field of some sort, whether it's a gravitational field, an electromagnetic field, that is actually causing them to behave the way they are. They aren't just doing it on their own. It's not magic, it is science, it's physics. Last one, letter F here, we have a block of iron moving towards a magnet. It looks like it's moving specifically towards the north side of a magnet. Iron being attracted to a magnet is again electromagnetism. The reason that magnet has a north and south side is because of the configuration of the electrons inside the metal. I won't say every magnet, but these north-south magnets, the ones that commonly have like the red and the white on the magnet, they have a different polarity due to the configuration of their electrons. Same with the Earth. The Earth has a north pole and the Earth has a south pole, and there is actually a strong north charge at the north pole and a strong south charge at the south pole, and those will flip. We have evidence to show that that has happened a lot in Earth's history, and it should be happening any day now. So we're just kind of waiting for that to happen. The magnetic north has started moving a little bit in the past couple of decades. So we don't really know how fast this is going to happen. But just because it moves a little bit over the past couple of decades, that could be a sign that it is starting, or maybe it has already started, and it's possible that it just takes a really long time for these poles to flip, and we're just experiencing the beginning of it. Or this is just a precursor, and this is kind of the Earth showing us a hint, like, hey, the North Pole is getting kind of irregular. This is going to flip. We don't really know what happens when it flips, because I don't believe humans were on the planet last time it flipped. I actually can't remember the length of time that it takes. Humans have been around for about 200,000 years, Homo sapiens as we understand them. So I don't remember if it's, for some reason, I think it was 60,000 years. But anyway, we don't know what's going to happen when those poles flip, but they will, and we will just have to figure it out when it happens. So those are some everyday interactions. Whoops. So these everyday interactions are mostly governed by gravity and electromagnetism. Almost everything that we talk about in this class is electromagnetism, the forces. We always talk about the macroscopic scale. Later on in the class, we'll talk about Newton's universal law of gravitation, which is a little different than anything that we're going to talk about in this chapter. But all of the macroscopic interactions that we're going to talk about here are governed by electromagnetism, like the contact forces we talked about above. Right? Okay, now forces on a smaller scale. We have this graph. I think it's a pretty cool graph. So this graph, if we look at it, I'm going to zoom in here so we can get a better look at this. So this is the force between nucleons. Okay, nucleons is another word for hadron. We're looking at the force between protons and neutrons, right? So the positive y-axis is repulsion. The negative y-axis is attraction. So we have this red line, which is the strong nuclear force, which is shown as short range, and then the Coulomb repulsion force. This is just the fact that positives will repel each other, negatives will repel each other, right? So that dotted blue line, you can see as it gets closer and closer together, they will start getting more repulsive right through here. But this, on the x-axis, is the nucleon separation. Okay? Now, nucleons are usually separated about here, a little bit over 1 times 10 to the negative 15th meter. So in this range, that is the typical point where protons and neutrons, or protons and protons, are near each other. Now, you can see that if things get really, really close, they get really, really repulsive, but they're usually not that close. Then you can see that that Coulomb force is going to get weaker and weaker and weaker because that works on a different scale. Remember, the electromagnetism usually works on, it's a longer range force. So as you look at that peak separation, right, this is right where nucleons are separated, where it peaks there, I guess where it valleys, right? That is where we have that key separation between protons and protons. And that is also where nuclear force is the strongest. So that is where we can see that there is this strong force between nucleons that is holding them together. Now, as they get further and further apart, you can see that that gets weaker and weaker. And if they get a little too close, again, that gets weaker and weaker. But if we look at that point here, where they are actually close together, that is where the strong force is actually its strongest, which is weird to say. Okay, so that is the connection between this graph and atomic structure, that the strong force is the strongest, it's its most efficient right where it's needed, which is interesting. right where the nucleons are separated, right? That's their normal, stable separation point. That's where the strong force is. It's at its most efficient, which is very convenient for our universe. Without that, things would be a little bit more chaotic. All right, now, so those are our fundamental forces. We're going to talk real quick about Newton's first law of motion. We'll go over a quick review, and then we'll end the video, and we'll do Newton's second and third laws another time. So Newton's first law of motion review. If an object is not subject to unbalanced forces, it could be A, at rest, B, accelerating, or C, at a constant speed. So remember Newton's first law. Right? Newton's first law of motion is that if an object is at rest, it will stay at rest, and if an object is at motion, it will stay in motion unless acted upon by an unbalanced force. Now, and there's Isaac Newton off to the side. He's got a pretty large nose, my goodness. He was a very, very smart guy for his time. Unfortunately, as he got a little bit older, he started getting a little crazier. This is due to his experimentation in, what's that called? Alchemy. Alchemists usually experimented a lot with mercury, and Newton started developing symptoms of mercury poisoning called Mad Hatter's disease, because people who made hats also used liquid mercury in the process, so they would literally go crazy. That's where they got the term Mad Hatter. But as Newton experimented more and more, he got crazier and crazier, which didn't help because he was already cuckoo. So he actually had mercury poisoning when he got later on in life. But enough about Newton. First law, if an object is not subject to an unbalanced force, it could be at rest, accelerating, or at a constant speed. So if we review the first law, right, so it's not subject to unbalanced force. So due to that first law, it could be at rest, or it could be at constant speed. So Newton's first law says that if an object is, so an object will, at rest, will remain at rest, A, and an object in motion will stay in motion, C, unless acted upon by an unbalanced force. So if it is not subject to an unbalanced force, it can't be accelerating. To accelerate, you have to have an unbalanced force acting on it. So real quick, let's talk about what is an unbalanced force. So in which case does a force not cause a change in motion? Right, so this is when forces are balanced. For a force to not cause a change in motion. But for a force to cause a change in motion, there must be this unbalanced force. Now, on Earth, we often have balanced forces. For example, myself, I am not accelerating, I am sitting still. But that doesn't mean that there are not forces acting on me. I have the AC gently blowing wind on me. That's a pretty weak force. I have gravity pulling me down, but that is opposed by the normal force of the chair. So those forces will balance out. I don't crush the chair doesn't launch me into space. Everything is nice and balanced. I just kind of sit still. Actually, I don't sit still. I keep moving all the time. I cannot sit still. So an unbalanced force is what causes acceleration. If I need to get up, I will push on the ground, and the ground will push back on me. That's Newton's third law. So if you need to, for example, when you accelerate in your car, when you're on cruise control, your cruise control balances the amount of force it's putting on the ground versus how hard it needs to go to stay at that speed. But when it needs to accelerate, you push on the pedal, you'll spin those tires more, put more force on the ground, then the ground will push you back, and you will be allowed to accelerate. Same for an object. Let's say you want to roll a ball at a constant speed, right? If you want to roll a ball at a constant speed, you kind of give it a gentle push and keep giving it a similar gentle push so that it continues that speed. Now, if you want to speed it up, right? If you want to accelerate it, increase the force that you're exerting. If you want to slow it down, which is also acceleration, that's just acceleration in the other direction, then you would exert a force on the other side. Those forces would be unbalanced, meaning there is no force to balance them out. We'll use that a little bit more as we go. So number two, when the forces are balanced is when a force is not causing change in motion. The type or the magnitude of the force does not matter if everything's balanced, right? For example, we have this massive planet that has a really strong gravitational pull that we're constantly under its force. However, our skeletal structure is able to oppose it, thank goodness. But even a simple chair is enough to keep me from falling down. Granted, gravity keeps me in the chair, but the chair keeps me from falling down as well. So it doesn't matter the type of the force or the magnitude of the force. If it is balanced, then there will be no acceleration, as long as you don't break the object, right? Now, number three, how are mass and inertia related concepts? This is a good question. So inertia is a characteristic of mass, right? So every object has mass, which means every object has inertia. So when you have inertia, let's talk about what inertia is, right? Inertia is it's the tendency to not change motion, right? Tendency, or you could say resistance to change motion. Sorry for the penmanship. So the inertia is basically every object wants to stay still. It's common for, not common, it's a law of physics that every object wants to stay still, or if it's moving, it just wants to keep moving in the direction it's moving. For example, my calculator has been sitting on this table the entire video. You guys weren't able to see it, but just proof, there is my calculator. It has not moved once this entire time. Matter doesn't want to move. Mass doesn't move. And its inertia is what makes it not want to move. It's just a characteristic of mass. Now, if that calculator were launched into space, then that calculator would move in the exact same direction in a straight line at the same velocity forever until gravity started changing that velocity vector, or if it ran into something. Now, on Earth, that's different, right? We are constantly under gravitational pull, so that will affect the motion of every object all the time. All motion in Earth's gravitational field will have a downward force trying to bring it back. And if you want to go up, you've got to beat that force. And you can do so with inertia, right? So more mass will equal more inertia. Now, let's see. If we have, let's talk about maybe football, right? Football is a pretty good example. If we have a football player, right? And we have a running back that is running at a linebacker, okay? Our running back running at linebacker. So the running back is obviously smaller than the linebacker. Let's say it has less mass. Now, as they collide, okay, the linebacker obviously has more mass, meaning he has more inertia. And without getting into the technique of football and tackling, that linebacker would be able to stop that running back instead of the running back causing the linebacker to move, right? If this guy has a lot more mass than this guy, then the linebacker has more resistance to change his motion. That means that the linebacker will cause an unbalanced force on the running back, and he will cause that running back to feel some acceleration. Okay? Newton's first law is a very important piece of Newton's laws of motion. All of them are very important, but Newton's first law is not going to find its way into our math in this video. In the next video, we will go over Newton's second law and Newton's third law, and we will do a little bit more math in that video.